Hi, my name is Nick Fitzes. I'm a PhD student from the Computer Graphics group of the Athens University of Economics and Business. This is a presentation of our work on Illumination-Guided Furniture Layout Optimization. Lighting, both artificial and natural, is one of the most important aspects of interior design. It affects the mood, the aesthetics, and the utility of the scene and its object. An apartment living room set needs a cozy lighting ambience. An office room requires workstations positioned under lighting conditions that favor uninterrupted work. Each furniture cluster can have very specific lighting requirements under different scenarios. We will show how lighting need not only be an afterthought, but can also guide an automatic furniture layout process to produce valid furniture arrangement. Furniture layout falls under the general category of inverse geometry problems. In these types of problems, we want to optimize geometry via parametric or direct manipulation driven by specific constraints and goals. Interior design specifically combines a selection of 3D objects, the geometry of the space to be populated, and a particular set of constraints and goals. Constraints with respect to space geometry, ergonomics, utility, safety, aesthetics, and illumination, which have been practically neglected so far. An automatic system should take these inputs and propose valid and optimal parameter states of the geometry with respect to these constraints and goals. Interior layout arrangement has seen great interest in our field. Many methods have been proposed over the years. There have been assistive methods, semi-automatic and automatic methods, methods based on object relationships, and lately, deep learning approaches. Still, lighting constraints have been largely neglected. Such methods can be very useful to an interior designer professional. Looking at a designer's pipeline, we have a selection of objects that need to be arranged under certain constraints. Lighting is a core aspect of this process, with each room or furniture cluster requiring different illumination levels in order to prove functional. In terms of constraints, a designer's thought process looks like this. As we saw earlier, there are many different types of constraints. Most of them can easily be described mathematically. Specifically for lighting, measuring the effectiveness of illumination in terms of task-specific target illuminance or intensity levels is an established procedure for professionals. Accounting for correct lighting is not always obvious. Illumination can drastically change the utility and effectiveness of a space. Consider the following example. At a glance, both setups seem to support the space's utility equally, a computer lab room. However, one setup does not account for any lighting goals and only respects geometric constraints. Without taking lighting into account, monitors in the first setup showcase extreme glare levels which will make the operator's job much more difficult and strenuous. We need a method that accounts for such lighting goals and integrates nicely in a designer's pipeline. In this work, we saw how to introduce illumination constraints and combine them with geometric ones in a unified manner that can be used to generate plausible furniture layout interiors in a wide range of scenarios. Our idea is directly applicable to the typical pipeline of an interior designer. For an arbitrary 3D space, the designer is responsible for providing the following: the geometry of the interior, the lighting setup, which includes ceiling lights, stand lights, etc., and windows and openings. Windows and openings are specifically required to account for natural lighting from the sky, dome, and sun, which are the biggest contributors when applicable. Of course, the selection of objects for the particular setup is also given. These objects can also include movable luminaires, which are elegantly handled by our proposed framework and can be used to complement existing stationary light sources. We need to respect an object's geometric properties in order to correctly position it with respect to the scene and other objects. Therefore, each object is defined by its bounding volume, calculated as its oriented bounding box, its facing direction vectors, which represent either access directions to the furniture piece or a practical site for alignment. One or more subspace intervals, which represent disjoint subspaces of valid transformations. All these properties need to be defined once for each object. Subspace intervals in particular allow to incorporate very tight and disconnected constraint spaces and are supported in our framework. This is a key aspect of constraint engineering in interior design. The designer needs an easy way to describe disjoint subspaces for the objects. This could be the different rooms of an apartment or the walls on which a cupboard can rest. Objects can also be grouped together into single entities. This allows for meaningful clustering of related objects, coherent move of related objects, optimization at both group and object level, intra-group exploration and optimization strategies. Groups have the same degree of freedom as objects and are seamlessly handled by our framework. Typical use cases for grouping is a dining table and its chairs or a living room set. The important thing to keep here is that objects within groups can still move in the group's local space, retaining all their individual freedoms and geometric constraints. And now that we've talked about how we define objects, groups, and their degree of freedom, we continue discussing how we incorporate lighting and geometric constraints. We support three types of lighting constraints through the use of illumination samplers. Samplers are used to measure illumination levels using physically based light transport solvers. Illumination targets and quantities directly map to an interior designer's workflow using photometric units. Our framework specifically uses looks and needs accordingly. Samplers can be attached to any object, therefore respecting its movement, or be freestanding. We define them separately from the object's geometry so that they can be easily transferable between scenes and scenarios. Firstly, we have planar samplers, used to uniformly sample illumination over a rectangular area. They are defined by their position, dimensions, and target illumination level range in looks. Next, we have directional samplers. They sample luminance over regularly divided strata of a frustum. We use the max of average luminances of each stratum as the representative value. They are defined by their direction, field of view, stratification factor of the frustum, and target luminance range in nits. Lastly, we have volume samplers. Uniformly sample luminance in a bounded volume. They are defined by position, extents, and target luminance range in nits. Here are some simple examples to better illustrate the utility of each constraint. The planar sampler is useful for setting target illumination levels over specific furniture pieces. Here, the table and bookshelf use a planar sampler. After optimization, both of them are positioned so that illumination targets are respected. Directional samplers are useful for suppressing the glare problem we saw in the beginning, as well as other generic directional luminance targets. Here, the desk and monitor positioning are optimized in order to minimize glare while maintaining adequate illumination levels on the desk surface through a planar sampler. Keep in mind that excessive glare can be caused both from direct and indirect lighting paths. Lastly, volume samplers are useful for setting average luminance and ambience targets in specific parts of space. In this example, we want to achieve adequate illumination in the space in front of the projection screen for the presenter. Complementary samplers are used to achieve pleasant illumination on the desk and low glare on the projector screen. Note how in all three samples, parts of space like the overbright spot near windows or underlit areas are avoided only by the specified lighting goals. There is no geometric constraint generic enough to handle these cases. It's important to also note that all three types of samplers require physically based light transport evaluators in order to correctly account for the wide range of surface materials and geometric formations like highly reflective surfaces, densely occupied environments, or openings with overhangs. Moving on, in terms of geometric constraints, we support distance, penetration, alignment, focus, and conversation constraints. They are easily defined with a valid range from a lower to an upper bound. Distance constraints are between the centers of two objects. Penetration refers to the amount of overlap between two objects. For speed, we use a voxelized representation of each object and use the number of overlapping voxels in our calculations. Alignment is evaluated with the angle between the facing vectors of each object. Focus and conversation are two very important functional constraints with respect to the utility of the interior. We enforce them through the combination of alignment and distance constraints. We wanted to allow for marginal violations of both geometric and lighting constraints in order to favor a wider exploration of the parametric space and reach optimal states in terms of illumination. We call them elastic constraints. The idea is to have a leeway region outside the bounds that still considers the state valid but with added cost. A distance constraint between a sofa and a TV set would be evaluated like this. Here, Bmax and Bmin are the constraints bounds. The formula we used is modeled after elastic springs, and the graph on the top right shows its behavior. This is a valid setup with zero cost, as the distance is between the bounds. This is a valid setup with added cost. This is an invalid setup that is rejected. Note that specifically for lighting constraints, there is no invalid region, since lighting goals could practically be unattainable under certain scenarios. The discussed formulation of both geometric and lighting constraints allowed us to combine them in a cost minimization framework with the following cost function. This is a very hard function to optimize. It is characterized by discontinuities, many local minima, a large search space, and the difficulty to sample valid states. We combine groups, subspace intervals, and a mutation strategy into a hierarchical Markov chain Monte Carlo process to meaningfully explore the large search space. Our mutation step uses one of four actions in random. Move and rotate actions generate states in the current subspace. Jump actions randomly choose a different interval subspace of the object and move there. Swap actions exchange the position of two entities only if their interval subspaces partially match. Here's an overview of the algorithm. Firstly, each object holds its current state, including position, rotation, and current subspace. Our algorithm works hierarchically, working from the group level down to the object level. At each step, a state mutation is sampled and the state is evaluated in terms of its geometric constraints. If no violations have taken place, the algorithm proceeds to evaluate the lighting samplers which are used to enforce the illumination constraints. Note that lighting is evaluated only for states that satisfy the geometric constraints because they are far more computationally expensive. Following is a clip showing our algorithm in action in a two-room apartment. Notice how both objects and groups make use of disjoint interval subspaces for meaningful exploration. Also notice how the individual freedoms of each object are respected, for example within the living room set, providing for radical but meaningful intra-group arrangements. And now, our algorithm in action. The following examples showcase automatically proposed furniture arrangements in different scenarios. All proposed layouts were reviewed by a professional designer. First, we have a proposed arrangement for the two-room apartment with 2 light panels and 3 windows. This is a well-lit room. The trickiest lighting goal here is glare avoidance. Our algorithm is successful in finding one of the few arrangements that minimizes glare on the TV screen while keeping the table and living room set sufficiently illuminated. Next is an open office space with 2 windows and 6 light panels. The system was tasked with recommending arrangements for 3 different primary office hours. Both desk positioning and monitor orientation were put under optimization. We wanted low glare on screens and adequate lighting on desktops. Characteristic is the morning scenario where direct sunlight near windows is avoided by all desks. However, the space is effectively used for the night and afternoon case. Next, we have an event hosting scenario. The available space around the dance floor is effectively utilized, while tables clear the overlit dance area. The clip shows proposed arrangements for 3 event hours during the day's progression. In both day and night sessions, table placement is guided only by lighting goals. Lastly, we incorporate 2 movable light sources in an underlit night scenario of the 2-room apartment. 2 stand lights are included in the optimization in order to complement the insufficient ceiling lights. The resulting arrangement achieves all target illumination goals with adequate lighting for the table and living room set, along with glare avoidance for the TV screen. One expected limitation of the method is that, whereas scenarios with attainable illumination goals converge quite fast, unrealistic or contradicting lighting intention may have a significant impact on both the conversion speed and the quality of the solution. Another missing feature of the current version is that we do not address any statistical illumination constraints over the planar and volume samplers, such as uniformity or minimum peak acceptable levels. Finally, stochastic processes are in general very dependent on initial seed and the constraint space. Future directions and improvements include the investigation of machine learning for light field encoding and preference-based layout proposition, since such approaches have produced promising results for scene synthesis tasks. To accommodate a wider range of user requirements and different design workflows, a broader use case study would greatly benefit our work. Finally, we are looking forward to extending our method for urban planning tasks where different sets of design guidelines apply. In conclusion, we showed the importance of lighting goals in interior design. Professionals have been hand-optimizing the layout, but since lighting goals can be explicitly described mathematically, we are able to incorporate them in an automatic system for layout suggestions. The 3 types of physically based illumination samplers we introduced to the layout problem can serve a variety of illumination goals, which can drastically affect the layout of interior spaces in ways that cannot be defined through other constraints. Our research group is actively researching several light-driven design problems. These include inverse geometry, lighting, and opening problems. Visit us online and get in touch with us. Thank you very much.